The state of the nearby planet group was once somewhat more on the raw side. Before it organized itself into a straightened plate, the circulation of residue and rocks shared something else for all intents and purpose with a doughnut than a flapjack. This is the end researchers arrived at subsequent to concentrating on iron shooting stars from the external nearby planet group, finding that they must be made sense of assuming the planetary group's shape was once toroidal. This is data that can assist us with interpreting other arising planetary frameworks and decide the request where they gather. The development of a planetary framework around a star begins in a subatomic haze of gas and residue floating through space. On the off chance that a part of the cloud becomes sufficiently thick, it will implode under its own gravity, turning as it goes, turning into the seed of a developing child star. As it turns, the material in the encompassing cloud maneuvers into a circumnavigating plate that feeds into the protostar. Inside that circle, more modest bunches structure, becoming protoplanetary seeds that either keep on developing into full planets, or, what appears to be undeniably more continuous, have their improvement captured, staying as a more modest item, like a space rock. We've seen these plates over and over around different stars, with holes cut via planets slurping up the residue as they go. Be that as it may, iron shooting stars found here in our own planetary group recount one more piece of the story. As per a group drove via planetary researcher Bidong Zhang of the College of California, Los Angeles. The piece of space rocks in the external planetary group requires the haze of material to be doughnut formed, as opposed to a progression of concentric rings in a level plate. This recommends that the primary phases of the framework's combination are toroidal. The iron shooting stars being referred to, lumps of rock that have made their long method for earthing from the external nearby planet group, are more extravagant in hard-headed metals than those tracked down in the inward nearby planet group. These are metals, for example, platinum and iridium, whose development can happen in an exceptionally hot climate, for example, one near a shaping star. This represents a cycle of a pickle, since those shooting stars came not from the internal nearby planet group, but rather the external, and that implies they probably framed near the sun and moved outward as the protoplanetary plate extended. As per displaying directed by Zhang and his partners, however, these iron items could never have had the option to cross holes in a protoplanetary plate. As per their computations, the relocation might have happened most effectively if the protoplanetary structure was toroidal in shape. This would have guided the metal-rich items towards the external edges of the shaping planetary group. Then, at that point, as the plate cooled and the planets began to frame, the powerlessness of rocks to traverse holes in the circle would have gone about as an extremely viable wall, holding them back from moving back towards the sun under the draw of gravity. When Jupiter shaped, it probably opened an actual hole that caught the iridium and platinum metals in the external circle and kept them from falling into the sun, Zhang says. These metals were subsequently integrated into space rocks that framed in the external circle. This makes sense of why shooting stars framed in the external circle, carbonaceous chondrites and carbonaceous-type iron shooting stars, have a lot higher iridium and platinum contents than their inward circle peers. It's astonishing what you can gain from a piece of hollowed metallic stone. The exploration has been distributed in the procedures of the Public Foundation of Sciences.